Welcome back. In this lecture, we will look at how does a semiconductor that is part of a semiconductor electrolyte interface, how does it absorb light, some features of this interface. Much of this must be familiar to you. Supposing you have semiconductor, you have the valence band edge here. This is the conduction band edge here. So the difference between these edges is called the band gap. So when a photon impinges on the semiconductor, if the photon's energy is less than the band gap, there will not be hole electron excitation. If it is just equal to the band gap, there'll be hole electron excitation. This is called an exciton. If the energy of the photon is much more than the band gap, there'll be a hole electron excitation. Initially, the electron would be in this position because there are a lot of closely spaced electronic energy levels available for the electron in this region. It will quickly relax back to the band edge. So this difference in energy would be lost as heat. Okay, so we'll see why we say it's an energy loss, because what we are interested is in converting solar energy to some usable energy form that can be electrical or some chemical work. So this excess energy of a photon beyond the band gap is not really usable. It is lost as heat. So there are different communities that specify energy in different ways. So the physicists and material scientists typically specify their energy in electron volts. I also prefer this kind of measure. For example, we say the band gap of, let's say, silicon is 1.1, band gap of TiO2 to zinc oxide is 3.2 electron volts. Okay, so lambda refers to the energy, the wavelength of photon. If the wavelength of photon is specified in micrometers, typically this kind of specification is done by, let's say, chemist. It is possible to convert the energy in EV using this formula. It's just good to have this in your mind, because two different communities would specify energies differently. If it is specified here in this manner, you may want to convert it to lambda or the other way around. So the energy of the photon decreases with increase in wavelength, or it increases with decrease in wavelength. So there is a critical wavelength of photon which is equal to the band gap. So that can be obtained here. Okay, so if the photon wavelength is longer than this, it will not give rise to an electron hole excitation. This is one feature. Another feature is that the extent of photon absorption increases with the thickness of the interface, thickness of the semiconductor, right? So the fraction of incident photon flux that decreases as the light penetrates more and more into the solid. So this can be mathematically represented in this manner. So this you might have seen in your high school experiments on optical absorption, proving the Beer-Lambert's law, right? So the rate of decrease of intensity with distance is proportional to intensity. This is the absorption coefficient, right? So this involves a decrease, so there's a negative sign here. So that can be integrated and you can get the Beer-Lambert's law, right? This is a form of Beer-Lambert's law. So if this is the light intensity indicated as the flux, photon flux per unit time. So if it's a monochromatic photon flux, this is the energy. So you can also convert this flux into watt per meter squared. This is the conversion, right? All right, let's move on. This is all just, many of this is just some useful conversion factors. An other important feature of semiconductor is the absorption coefficient. Why do some semiconductors have greater absorption coefficient? Why do some others have lesser absorption coefficient in general? This is critically to do with whether a semiconductor has a whether it is a direct band gap semiconductor or an indirect band gap semiconductor. Before proceeding, if you're unfamiliar with this, at least take a look at these two Wikipedia links. There's a very good link on electronic band structure. This link on direct and indirect band gap semiconductors. So again, we are plotting the energy in the y-axis and the momentum or the k vector of the electrons is specified in the x-axis. So in a direct band gap semiconductor, the maxima of the valence band, that is the edge of the valence band, is in the same position, as the same momentum as the minima of the conduction band. This is the conduction band minima, this is the valence band maximum. So there can be, when a photon impinges, let's say at an energy equal to the band gap, the photon excites an electron hole pair at the same momentum. That is the momentum of the electron in the conduction band is same as the momentum of the electron in the valence band. Okay, so if this looks like a jargon, some exposure to solid state physics or material science is useful, where you understand what is called a block wave, a block state, and so on. Please look at least these two Wikipedia links to understand what exactly do we mean by this. So in a indirect band gap semiconductor, this is the valence band maxima, but the conduction band minima is at a different momentum state. So there are additional constraints have to be satisfied to conserve momentum. So there is this transition between the valence band to the conduction band, transition of an electron from a valence band to a conduction band has to be assisted by the lattice. This is what we mean by phonon assisted transition. If this is not clear, again, at least look at this link. I mean, you need not understand the details. All you need to know is because of this constraint, the absorption of an indirect band gap semiconductor is lesser. Unfortunately, silicon is an indirect band gap semiconductor. Therefore, the thickness of silicon that has to be used for absorbing photons is in general greater. Okay, so in this plot, what we are plotting here is the absorption coefficient along the y-axis and the photon energy along the x-axis. There are two semiconductors which are indirect in nature. Silicon is an indirect band gap semiconductor. Cadmium telluride is also an indirect band gap semiconductor, whereas germanium and gallium arsenide are direct band gap semiconductor. So the direct band gap semiconductors are in general have a greater absorption coefficient. For some of the direct band gap semiconductor, let's say gallium arsenide, will have other problems. Handling arsenic is very challenging. So this arsenic is poison. So material processing of gallium arsenide is in general difficult. Okay, so let's get on to solar energy conversion to electrical power. Okay, so supposing you do this via a solar cell or a photoelectrochemical cell. How to do it in a photoelectrochemical cell will be addressed in the next lecture. But let's just consider some common some general themes. We have already seen the meaning of this schematic. Where do we get the solar energy? So solar energy is obtained from the sun, which is a black body at around 5000 Kelvin, right? So the black body spectrum of the sun is fixed by its temperature. So what do we see here? Along the x-axis, we plot the photon energy. Along the y-axis is the power density at a particular energy. What we see here is the peak is obtained in this photon energy, right? So which is more than, let's say, 2.2, 2.4. This is where the maximum amount of photons are present. Beyond 4, there are hardly any photons. Below this, there is hardly any photons, right? So ideally, your semiconductor should be have capacity to absorb photons in this region, right? So what is the question we are asking? We are interested in percentage of incident light energy that can be converted to, so that's what is plotted in the y-axis here. Along the x-axis is the band gap of semiconductors. So you don't have a flexibility here because this is what you get, right? This is the solar spectrum that you get, but you have a flexibility in what kind of semiconductor that you can utilize for solar energy to electrical power conversion. So what is the main feature we want to tune? It is the band gap of semiconductor. So supposing you have a semiconductor that has a very small band gap. Of course, you can absorb most of the light because most of the solar energy photons have greater energy than the band gap. However, because of this process, relaxation to the band edge of the conduction band and release of heat, much of the energy that is obtained from solar photons is not utilized for useful energy, right? Much of it is lost as heat, right? So if you have very low band gap for a semiconductor, the percentage of energy that is lost while the photon, while this electron relaxes to the conduction band edge is more. As you increase the band gap of a semiconductor, very few electrons will be present in a region that is much further than the conduction band edge. So the energy lost as heat decreases as you increase the band gap of the semiconductor. So that explains the green part of this plot. So here what is represented is as you keep increasing the band gap of semiconductor, lesser and lesser photons have greater energy than the band gap, right? So when you have small band gap semiconductor, most of the energy, most of the photons can be absorbed. There are very few photons, okay, that cannot be absorbed. But as you keep increasing the band gap of semiconductor, the number of photons that have lesser energy than the band gap increases. So there are other losses too, which is we are not going to talk here. Okay, so that involves the other features involving current and so on. So that is not going to be discussed in detail, but these two features, that is heat loss, energy heat that is lost as heat was discussed, and the amount of photons that have more than the band gap, that is also indicated by this yellow region. So the useful region that is involves semiconductors that have band gap somewhere here, right, in this region. Fortunately for us, the band gap of silicon, which is about 1.1, is in this region. So the usable electrical power increases than decreases. Okay, so there are two reasons, right? It increases because the amount of energy loss due to this relaxation that decreases with increase in band gap, but it decreases because as you keep increasing the band gap of semiconductor, lesser and lesser solar photons can be absorbed. So this kind of trade-off, what do you mean by trade-off? Typically in engineering, when you increase something, something else decreases. When you increase the band gap, this heat loss, energy loss decreases, but the amount of photons that can be absorbed decreases. So that's the trade-off. So your optimal property is somewhere in between. So this is an important feature. Uh, uh, there has been a lot of analysis for different semiconductors. Uh, so you should be aware of the meaning of this plot schematic. In the next lecture, we will look at some other features of electrochemical cell. Thank you.